Hi there, Pre-Calc students. This might be one of the last videos that I'm going to be recording this year, and so you're probably tired of me anyway, so that's good. Anyway, this is Limits 4A Rates of Change and Tangent Lines. This is really kind of the backbone of calculus, at least one branch of calculus, as you can see. So we're going from average rate of change to instantaneous rate of change. And notice as it says here, this average, anything rate of change is just a huge part of calculus. And average rate of change, amount of change divided by the time it takes. So we could think of it as the change in y divided by the change in x. And of course that should sound very familiar to you because the change in y divided by the change of x is simply another name for slope. Slope is the change in y over the change in x. So anyway, let's just take a look at an example here. A rock stands for the average rate of change, x cubed minus x over the interval 1, 3. So again, basically what this is a change in y over a change in x. And we're going to write it a little bit different here. I'm going to write this as the f of 3 minus the f of 1, all of that over plain old 3 minus 1 like this. And as we can see by our table here, the f of 3 right here would be 24. The f of 1 is 0. And of course 3 minus 1 is 2. And so I'm going to get 24 divided by 2, which will equal 12. That's the average rate of change. Don't really have any units here that we can talk about, but that's the average rate of change, very similar to slope. All right, and yeah, the slope of the secant line is basically what we're talking about here. And a secant line is a line that just goes exactly from, let me change my color here, from where the point 1 right there is to 3, which would be up here. And the secant line then looks something like this, and that average rate of change then is the slope of that secant line. So we can see from this diagram here, secant line between those 2 points like that. Now the tangent line then, you may remember tangent from your days of geometry. Tangent, we talk about tangent as a trig function, but tangent is also known as a line that just sort of grazes a point on the graph just like this. So that's the tangent line. And of course we have our same slope, change in y over change in x. There's that tangent line slope. Now, here's the crux of the issue here. We are defining slope of a curve at a point. Now, notice how significant this is. Up to this point, you have found the slope of a line, but you've needed 2 points in order to do that, just like we did with that average rate of change. Now we're actually going to be able to find the slope at a point. Very, very significant. Now, this diagram will help us out a bit, I think. F of x plus h minus the f of x. Well, really, those are just two y values. The f of x plus h is a y value, and the f of x is a y value. And our two x values then are x plus h and x. Now, if we subtract those, the h or the x's kind of cancel out, and we get h. So really, what you should see here is that this is really nothing more than a glorified slope equation, basically. This will represent the change in y. This represents the change in x. Now, what is this all about? This is h goes to 0. Well, we want this h distance to keep decreasing, so essentially we're going to end up with the slope at a point. Hi, Puma. What do you have to say? You're trying to help me here a bit. All right. Try one example using this, and this will be a fairly basic example, but should suffice, I think, for our purposes here. Let's see, I guess I'll use this pen color. So again, what this is the limit as h approaches 0 of the f of x plus h minus the f of x, all of that over h. Alright, boom, I get out of the way now. Alright, so let's just think about this. So that means that I have to put this x plus h right here, I have to put that in place of this x. So what that's going to give me is x plus h squared minus the original function there, which is just x squared, and all of that over h. Now I could or should really keep writing all this limit stuff, but I'm not going to do it. Now if I square this out, FOIL this out if you will, I'm going to get x squared plus 2xh plus 8 squared. That's just this much right here. This much multiplied out gives us this. And then I have to subtract x squared. Keep in mind that's still all over h. Alright, now notice, and this will frequently happen, I can cancel these x squareds out. So what I have left then is 2xh plus h squared, all that over h. Now can I do any reducing here? Yeah, I can. I'm going to look for a common factor over here, and this has a common factor of h. So I'm going to pull that h out of there, and then I get 2x plus h. That's all over h again. Now you see that I can cancel out these h's, and so what I really have now is the limit. I haven't been writing this limit down, but it's still there. The limit as h approaches 0 of 2x plus h. And because h goes to 0, like this, h goes to 0, basically then we're going to call h equal to 0, and so my final answer here then becomes 2x. 2x. Now if I want to know what the exact slope is when x equals 1, as they say here, all I have to do is put 1 in place of this x. And therefore my final answer that I want here then of course will be 2 times 1, which is 2. So notice how significant that is. What I just did enabled me to find the slope of this particular function at a particular point. And as we will talk more about that, that's the slope at a point. It could also be thought of as instantaneous rate of change or instantaneous velocity. All kinds of good stuff spring from what we just did here. Alright, we'll continue to work on this in class. This will be a big thing that we'll have you do on a test to see if you can find the slope using this definition just like this. Alright, thanks for listening, and we'll see you guys in class.